Any questions that, or any comments that, do you have any questions or comments on what we did last time? Okay, so I will be continuing in the same way. Last time, if you remember, we talked about very simple deterministic models, EOQ structure. Now I think it's time to move on and talk about some stochastic demand inventory problems. Now this is going to be, of course, a very basic problem. I will start talking on the news vendor problem. And the way that I'm going to pose the news vendor problem will be almost in its standard way, but I think it is going to be closer to the way that it is described in Silver et al. And this problem is sort of the problem which forms the basis for most of the analysis that you are going to see in this course. Okay? Now, there will be, of course, some extensions of that, but it is a very simple structured problem where you can add certain things on and you can play with it. So we need to learn this very well. You're going to see that we're going to have some homework questions related to that, and I usually ask questions in the midterm about this simple news vendor problem, some little extensions that I place, so on and so forth. So this is sort of the, let's say, the knowledge that you need to go ahead in this course. Now, you are already familiar with that, but I want to spend some time on the review of this model. Now, the news vendor problem is a single period stochastic demand problem where you place an order in the beginning of every period and the problem lasts only a single period. There are many problems that fit this environment, and the newspaper problem, the quantity, how many newspaper to order every morning for the news vendor, this is called the news vendor problem, is a typical problem of that sort. Because basically a newspaper is only going to be valid for that day. It's not going to be valid next day. In other words, you cannot sell yesterday's newspaper today. It's not going to have a lot of worth. Although sometimes it might, okay, and maybe we'll give some reasoning for that. But in general, the news vendor problem is very simple. Today is a certain day, and how many newspapers should I order so that I will maximize my profits as the news vendor? Now, what are other examples related to this problem? The typical problem is the problem where you sell certain product in a season, and then there is no value of that product. And the typical example will be style goods. Now, what do we mean by style goods? Style goods are the goods which are fashionable in a certain period, and then once the fashion is gone, you're done with it. Think about a lot of swimming wear that you have in the summer period. This is especially for women. But the idea is that you have a certain fashion that year. So there is a huge manufacturing which is done prior to the season, which means that the manufacturing is going to be over around March, April. And then you sell the product that you manufactured for the summer period. And it's usually the case that you don't have a chance of making a second manufacturing run for the product that we're talking about. Now, of course, in the news vendor problem, we're aware that although it might be very costly, they can make actually a second run. In other words, think about the situation where you have a very important thing going on. I think this usually happens during wartime. Okay, so you printed the newspaper, and at 8 o'clock in the morning, you heard that there is a new war going on. So what you do is you make another print. It's another newspaper, actually, and you sell it in the afternoon. Okay, but this is very rare. And you can also consider that as another period anyhow. So in the style goods case, the setup of manufacturing is very expensive, so you only set it up for once prior to the season, and you expect to satisfy the demand and make some profit. So this is called style goods or the news vendor problem. Now, a number of parameters which are in question is, let's say that we have a V, which is called the acquisition cost per unit. In other words, for every unit that you manufacture, this is going to be the cost. Let P be the revenue that you obtain per unit. Let B2 V, now I'm going to call this B2V because of the following reason that I'm going to explain. This is the penalty for not satisfying demand per unit. So if you cannot satisfy the demand, we think that there is a penalty associated with that. Now, of course, the way that I am going to pose this is not going to be necessarily all the time this way, but it's usually written as a certain value times the value of the item that you cannot sell. For example, this is very much true in the style goods industry. So if you go to Beymen and you're looking for something which is designed by Rıfat Özbek, okay, which is very expensive, exclusive, okay, you really want to buy it, but your size is not available for one reason or another, and you are sort of a standard size. Okay, if you have a size like me, then it's not going to be standard, and you won't be able to find it anyhow. But let's say that you have a standard size. And if you are a good customer, this means that in order to compensate for that, they are probably going to give you something else as a gift. So you're not only going to lose the probable profit that you were going to obtain, but you are also going to give a penalty. And that penalty is going to be probably as a function of the product that you are going to sell. You were going to sell if you had it. So that's the reason why we usually have the tendency of writing the penalty cost this way, but without loss of generality, you can call it B2. Now, B2 is a specific notation which is used in Silver et al. Because there are other possible type of backorder costs that we don't need to talk about actually here, but that's the reason why it's B2. There is also a B1, and then he has a B3, and so on. I simply wanted to follow the notation in the text. Okay, and finally, we are going to have a G, which is a salvage value. Note that the salvage is usually a value. It is not going to be a cost. In other words, if you cannot sell Rıfat Özbek's creation that season, you won't be able to sell it somewhere else. Now, depending on the product, you might have a secondary market for those products, but not probably for the style good example that I gave. You don't have a secondary product for very exclusive products. But if you have a brand name, you have some secondary markets that you sell the product. Or what you can do is you can simply lower down the price and try to sell it. Now, in the case of newspaper, you recycle the paper, and there is a certain value associated with that. Now, what happens if the value is negative? Okay, then it means that you have to pay something to get rid of the product. Now, there are certain products which work that way, not necessarily in the single period environment that we are talking about, but if you have, for example, batteries that you cannot sell at the end of the lifetime of the batteries, okay, then it's not going to be very easy for you to get rid of those batteries. You don't have a secondary market. Moreover, you need to pay some extra money to get rid of those batteries. Okay, so there are different examples, but usually we expect G to be a value, and of course, that value is going to be less than the acquisition cost. Because if it is larger than the acquisition cost, we will be sort of buying that product without any concern and salvaging it to a profitable margin. Now, in these type of problems, we usually represent the demand by a probability distribution. So demand during season, and we usually call it season, is basically represented by f of x. This is the cumulative probability function for demand x, and f of x is the PDF related to the same thing. Now, the question here, what is the decision problem that we are concerned? We are concerned with the decision problem of deciding Q. This is the decision variable, and question is, how many units should we order in the beginning of the period so that we will be maximizing our expected profit? Now, in the standard news vendor problem, the objective function is taken as the expected profit, which may not be the case for the single period problems. Now, think about these days. In these days, if you are selling continuously products which are consumed in one season, you are a textile industry, your aim wouldn't be to maximize the profit because we have some kind of a depression, economic depression. So what do? We probably have different objective functions. Like, for example, we might like to maximize the risk, minimize, the risk of losing money. So then what will happen is that the quantity that you are going to buy is going to be a little bit less because you are trying to make sure that you are not going to lose any money. Okay? So this objective of maximizing expected profit is not necessarily the only one. And however, in general, we expect that this is the main motive of the firms which are operating. Now, there are versions of the news vendor problem where you're going to have different type of an objective function. Now, in these type of problems, the approach would be as follows. Of course, we are going to write the expected profit function, and then we're going to maximize. You are already familiar with that. But the way to pursue these type of problems should be a little bit more systematic. In other words, you should be a little bit more careful in writing the profit function first, and then converting it to the expected profit function, and then the maximization is a standard procedure. It's more technical procedure. So we're going to do it step by step in the hope that if we have a more difficult structured problem, okay, which is going to be a little bit more complicated, it's not easy to distinguish between costs, profit, returns, but we would be able to write it in the same neat form. So what I will do is I will define a function PQ given x0 as the profit if Q units are ordered and x0 is the realized demand. So what I am doing is simply I am going to the end of the season, assuming that there is a certain demand which is realized, and assuming that I already have decided, committed for Q units, and I am simply going to compute the profit. This is not going to be the expected profit, but this is the realized profit. So in that respect, let us write the realized profit then in terms of the problem parameters. Now, it turns out that the realized profit is going to have two different regions depending on Q being greater than the demand or less than or equal to demand. In other words, if you ordered more than the realized demand, what will happen? You're going to have some salvage going on. If you ordered less than the quantity, if you ordered, I think I probably made a mistake. If you ordered more than the demand, you're going to have some inventory carrying, and it means that you're going to salvage those at the end. If Q is less than x0, it means that demand exceeded the quantity that you ordered. We call this excess demand. You're going to lose some probable profit. Moreover, you may also pay some penalty cost. So we're going to reflect that to this equation. So the first range would be if Q is greater than or equal to X0. Now, I'm going to pay the acquisition cost. So I will have minus Q times V. And then I will sell all the demand. So it means that I'm going to have a revenue P times X0. And then there will be some leftovers. And for those leftover quantities, I'm going to get some salvage value. So what is the number of those units which are left over? It is simply Q minus X0. And I'm going to multiply that with G, which is my salvage value per unit. So this is going to be the profit that I have. Now, on the other hand, if Q is less than X0, in other words, if we have excess demand, I am still going to pay an acquisition cost of QV. And what will be the profit that I'm going, the total revenue that I receive? I can only sell Q units. Although demand is larger, I can only sell Q units. So I'm going to have P times Q as my total revenue. But unfortunately, for the excess demand, I'm going to have some cost that I'm going to pay to satisfy my customers. So this is simply going to be X0 minus Q. Okay? Just let me make sure that this X0 is actually a lowercase. It's not I'm trying to write a little bit bigger, but that is going to be a lowercase x. Okay. Now, so you can see that for different X0 values for a given Q, you are going to have different possibilities. This is my realized profit function. Now, once I have this, to move from this point to the next point where I write the expectation will be simpler. How am I going to do that? Well, now let me define E of P of Q as the expected profit function. So now I can write the expected profit function. And the expected profit function in general is what? You take the expectation of this function. So what do we mean by taking expectation? If you recall the definition of expectation, you have the density function. Okay? And in front of it, you have the profit function. And you integrate that over all possible regions of the density function. So what does this mean? It means that I'm going to take this upper part of this function and integrate that for x values, which are less than or equal to Q. And then I'm going to take this part and integrate them for x values which are greater than Q. So in that respect, it is going to be straightforward. So expected value of the profit in general can be written as P Q given x, f of x dx, where this is the profit function for every value of x. Or if I am a little bit more precise, this turns out to be the integral from 0 to Q. Okay, this is the place where demand is less than Q. I'm going to have minus QV plus Px plus G times Q minus x. F of x dx is going to be the first term. And then I'm going to have the second term, which is the integral from Q to infinity. If I have excess demand, I'll have the second part, which is minus QV plus PQ minus B to V times x minus Q f of x dx. Now, what we are doing conceptually is when we are taking the expectation is very simple actually. We have this probability measure that we have here on the space, and then by taking the expectation of a certain function, we are sort of moving everything to the so-called deterministic space. Now, if you have this function and you want to maximize this function with respect to Q, it is nothing different than what you did in very basic calculus courses. It's exactly the same thing. Now, the only thing which is different is that you have a little bit more complicated function with integrals and so on, but the minimization of this problem for Q values, if you don't have any constraint, is going to be very straightforward. Okay? So you simply take the derivative of this function and equate it to 0. So the optimal Q value should satisfy that condition. And you take the second derivative, check whether the function is concave, convex, undetermined, or whatever. And depending on that, make sure that the solution that you found is the maximizing solution, or might be the minimizing solution, or one of the local optima, which means that you need to check all those local optima to find the global optimal value. Sometimes you can check it, sometimes you cannot check it, you will never know this. Okay? But these type of functions, it turns out that in the Nusswender function, expected value of P of Q function is a concave function of Q. How do we know this? Well, we take the second derivative and we find out that it's a concave function. It's very clean and neat. So, and basically, we know that any solution which is, well, the solution that is going to satisfy the first order conditions, which is take the derivative equated to 0, is going to yield the optimal solution. Now, anybody here who is not familiar with taking the derivative of a term which contains integral? Are you all familiar with that? Okay. Now, if you are not familiar, then there is this so-called Leibniz rule that you can use and simply solve for the derivative. Now, just for this case, let me take the derivative of that term so that we will simply solve it. Now, it turns out that the construct that I have done is the very basic construct that you have for most of the multi-stage, multi-level inventory problems. Because what happens is that even if you have, for example, consider dynamic programming. Anybody who is not familiar with dynamic programming? Are you familiar with dynamic programming? Okay. Now, what you have there is a multiple number of stages. Okay? So for example, this is stage 1, this is stage 2, and this is the way that the problem proceeds. Usually the numbering is a little bit different. Now, if you have a Nusswender type problem here, the solution is, if you tell me what the problem conditions are, then I will be able to find you the optimal Q value. Now, it turns out that if you are trying to decide on the Q1 value here, it is not going to be as easy. Because what you have is now you have to look at ahead and find out what will happen if I make this decision. And if this demand happens, there is a certain optimal reaction that I have in this period too. Now, even when you look at this problem, this Nusswender's structure is going to be kept here. We are going to see this as which is a result from 1960s. So it turns out that this structure is extremely powerful. There are a number of very close to optimal approximations using this structure for very complicated multi-structure or multi-level structures. Okay? There are certain papers related to that in our syllabus. So it turns out that looks very simple problem turns out to be one of the key problems that you need to know to go further. Okay, so now next step is let me take the derivative of this term, Okay, and so what happens is that when you take the derivative of this term with respect to Q, you simply apply Leibniz rule. Which is you first, there are three terms in this rule. The first term is you simply take the derivative of the upper bound, okay, and plug the upper bound into this functional form and write it. And then the second term is you take the derivative of the lower term and plug the lower limit into this x that you see here. And the third term is you take the derivative of the term that you are integrating. You still keep the integral limits in the same way. But here, instead of this term here, you have the derivative of that term with respect to Q. Okay? So if you do this, we are going to obtain the following. So let me start step by step. And this is basically the derivative of the upper limit is 1. So I'm going to have 1 times, so instead of x, now I'm going to place q. So I will have minus qv plus pq plus, well, that term is going to vanish, times I will have f of q. And then when I take the derivative of the lower limit, it will be 0. Okay? And then the integral will be kept as is, but I'm going to take the derivative of this term with respect to q, so I will have minus v plus g f of x dx. So this is the first integral. And then for the second integral, the derivative of the upper limit is 0. The derivative of the lower limit is going to be 1. So I'm going to have minus qv plus pq, okay? And then instead of x, I'm going to substitute q, so that term is going to vanish. I'll have f of q. And then finally, I'm going to have the integral from q to infinity of minus v plus p. And then I am going to have plus b to v f of x dx. Where's the x value? Q, v, p, q. And I will have, okay, yeah, x value is gone, and this is what I have. So as a result, this turns out to be the first order condition. Okay? I think I made it probably correctly. I sometimes make mistakes. Now, it turns out that when you look at these terms, these two terms are going to cancel each other. So we are going to be left with these two terms. And this is sort of a cumulative function of x. And this is a complementary cumulative function of x. So if I bring all the terms together in terms of the cumulative function, so I'm going to obtain the condition where f of q minus v plus g plus v minus p minus b to v is plus b to v plus p minus v is going to be equal to 0 at optimality. So from here, I can write the optimal solution, which is f of q optimal is equal to p minus v, plus b to v divided by p minus g plus b to v. So those two terms are going to be cancelled, and this is what we have. Now, what is the meaning of this? Maybe you remember this. Sometimes we use Cu plus divided by Cu plus Co. In the undergrad text, usually you have this term, which is cost of underage divided by cost of underage plus cost of overage, which means that cost of underage is the cost that you are going to have per unit if you have excess demand. And the other one is cost that you are going to incur when you have 1 unit over the demand. Now, what is cost of underage in this case? Well, you see that when you cannot satisfy the demand, you lose, number one, the profit that you were going to make. What is the profit that you are going to make? V is the acquisition cost, P is the unit revenue. P minus V is the profit that you were going to make if you had that excess unit. Okay? And what is B2V? B2V is the penalty that you pay for each demand that you cannot satisfy. You not only lose the profit, but you pay a penalty. So basically, the sum of those two is going to give you cost of underage. It is the cost of not satisfying the demand. Okay? Now, similarly here, this term is cost of overage. We can obtain cost of underage from here, and it's the same logic. Okay? For each unit that you are under, you are going to incur a cost of V minus G, actually. Okay? You are going to pay the acquisition cost, but you are only going to get a certain amount back. The difference is going to be the cost that you have for each unit that you cannot sell. You buy, but you cannot sell. Okay. So this is basically the solution. Now, the way that we are going to interpret this solution is as follows. So here, let us draw the f of q function. F of q is actually a cumulative function, probability function. So what we are doing is we are stocking up to a level where this function is equal to this specific ratio. So note that this ratio is going to be closer to 1 if Cu is much greater than Co. It means that if cost of underage is very much larger than cost of overage, I will have a tendency of stocking a lot. Otherwise, this is going to go, I shouldn't say to 0, but usually somewhere around 0.5 if the cost of underage is also a comparable quantity to cost of overage. Okay, so basically this is the picture. This solution is called the fractile solution. Okay, you have some kind of an optimal fractile that you set or you try to achieve when you are doing production. Okay. So this is basically the structure. Now, the value of the expected profit at optimality is also important. Sometimes you need to evaluate that, especially if you are talking about a multi-level problem. You will need to evaluate this. So basically what happens is that, remember the expected, we have written the expected profit function here. Now this is sort of a very crude way of writing it. You can write it in a more neat forms, in different forms. And one of the neat form that you might have is as follows. In other words, if you rearrange the terms, the integrals and so on, this is going to be the form. P minus G times mu, I will explain what this means. V minus G, well, let me say times Q. And then I'm going to have minus P minus G minus B to V plus B to V times X minus Q. Well, let me take this little bit here. Times the integral from Q to infinity, X minus Q, f of x dx. Sorry about the mess, but let me clean this. and simply say that this is Q star, so that I will have this form here. Okay. So if you rewrite the terms, this is going to be what you get. So what is mu? Mu is the expected demand. So basically your profit is going to be, this assumes that, well, the structure actually is such that if you sell the expected demand quantity, this is going to be what you get. And then at the top of that, you are going to, if you have excess, then you are going to get some kind of you are going to pay some kind of a salvage. And then here, this term simply is the penalty term that you pay, whether you deviate under or over it. So this is the form that might be useful. And if you had this form in the beginning, to take the integral would be much, to take the derivative of the integral would be much simpler, of course. In other words, we didn't have that. We simply wrote the integrals, took the derivative. But this is the general form. And at optimality, in other words, if you plug the value of Q star here at optimality, this term is going to become even much more simpler. At optimality, this is going to be minus B2V mu plus P minus G plus B to V, the integral from 0 to Q star, okay, x f of x dx. So basically, all of these are manipulations. I mean, there is nothing serious in that. You sit down, you manipulate the integral terms, and you simply plug this value in it, and this is what you are going to obtain. So you see that your expected profit can be written in different ways, but this is at optimality, this is going to be the solution that you have. Now, if I were you, I would sit down and simply try to see that these are actually realized. So take the same problem, try to write the expected profit function in this way, and then once you write it in this way, okay, plug f of q star in it, and see that this is the term that you are going to obtain. Okay? So these are some exercises I think you need to make if you want to make sure that you understood what's going on. These are very routine exercises, of course. Okay. Now, this is a very simple structured problem. Now, what do we learn from this problem? Actually, we are going to learn a number of things from this problem. And what I will explain you now is typical inventory policies using this simple structure. Now, we have already seen one of the inventory policies here. And that inventory policy is simply order up to inventory policy. So the news vendor problem, although it's a single period, you can make some generalizations, like we really like to do in the case of EOQ. Now, the policy that we are applying can be called an order up to Q star policy. Okay? Now, this is one of the policies that you have in the stochastic inventory problems. We're going to have other policies. Usually, we have the form as order up to S. We usually call it S as a certain value which you really want to shoot up to. And so what happens is that this level is such a level where even if you have starting inventory, okay, if you have starting inventory, you really order a quantity so that you want to make sure that you start with Q star to the new period. In the new period, you start with Q star. So this is basically what the meaning of this policy is. So if you have, this is the Q value, and here we have expected P of Q, and this is a concave function, as I mentioned. The optimizing point is the Q star, Okay? So what happens is that if your starting inventory is anywhere here, you order up to Q star. Oops. You're right. Okay, we are talking about profit function. Thank you. Somebody immediately raised his hand. So, okay. So this is basically the Q star value. Thank you. Okay. So this is the maximizing value. So what happens is that if you have a starting inventory which is here, okay, you want to shoot this level so that you will maximize your profit. Now, given the problem structure, this is going to be the optimal solution. Now, another way of writing the same problem is to convert everything to costs, as I told you. So in that case, you will be minimizing the total cost. And it's exactly the same problem. You simply manipulate the terms from here to there. Okay, so this is what we have. Any questions on this? Now, let's take a break, and after the break, I will try to make some generalizations using this problem structure and start extending it a little bit. Questions or comments? Okay, I'll see you after the break. Thank you.